Before we get started, if you haven't subscribed to the channel, please consider subscribing.
We will take a look at the efficiency of the OLS estimator by looking at a simulation study. So this is basically a typical problem set that you might have in one of your assignments. So it'll be a good idea to go through this exercise and implement this in R. So this problem is telling us first to generate 30 observations from this model. So we are basically taking independent draws from the normal distribution to generate some dependent variable, which is our x variable here. We will also take random draws from a normal distribution, which will be our errors or residuals after we estimate them. And then we will assume a beta of 1, and using this model we will generate our independent variable, which is the y variable here. And then we will estimate the OLS estimator using the x prime x inverse 1 x prime y formula that we know for the OLS estimator. And then we will estimate a different estimator, which is the beta tilde here, which is given here. And the whole idea is to repeat this thing a large number of times. In this case, we will do 10,000 times. Every time we will estimate a different beta for a different sample that generates, and then we'll store them in an object. And later on, we will plot histograms to see what the distribution of the two different estimators looks like. And we will take a look at whether one estimator is more efficient than the other. I'll go through this part by part and explain all of the different bits here. So first, we start with a seed. We set up all of the basic parameters that we have. So we want to do 10,000 times of repetitions. Every sample will be of size 30, and then we have a beta of 1. Great. And then part A, we have to generate the dependent variable and the errors. So x equals to r normal from a mean 0 and a variance 1. And then u is also going to be generated from a normal distribution. So r norm is the command, n is the number of sample size that we have already set to 30. And then we are generating y equals to beta. So beta here is 1 times x plus u. Okay. And we can display the output. And here we can see we have our 30 observations that's generated for y. We can also take a look at what values of x have been generated, what values of u have been generated. Now the next step that we are asked in this problem is to estimate the OLS estimator and then to also estimate this alternative estimator that we are calling beta tilde. So let's get ahead and do that. So because we have only one estimator, only one variable here, one dependent variable here, so the x prime x inverse 1 x prime y formula, that very simply becomes just x prime x divided by, x prime y divided by x prime x when we have only one variable. And so we can just simply do beta OLS is x times y divided by x times x, and then we sum it across all the variables, all the observations. And then the definition of beta tilde is given as x cubed times y divided by x to the power 4. We can go back to this problem and we can identify this. So here I can type out BOLS and I can see what is the estimate for the beta using OLS, and I can also look at the other estimator and you can see it comes up with a different estimate. Great. Now the next thing here is our simulation that's starting up, and that's repeating this thing 10,000 times. So first of all, I start up by creating two objects that I'm going to use as containers to contain and store the results for each iteration. And this is just a repetition of zeros, r times. We defined r as 10,000, so it will be just 10,000 zeros stored in each of these two different objects. And here is a loop that will be doing the simulation. So for I in 1 to r, so it will start iterating from 1 and it will go all the way up to 10,000, where r is equals to 10,000. Every time it's going to generate x equals to r normal from a normal distribution with n sample size, which we have set 30, mean 0 and variance 1. It's going to draw error u. It's going to define y in this model, as per this model, and then we are going to store the ith value of this object equals to the covariance of x and y divided by the variance of x, which is the same thing as what we did here, sum of x times y divided by sum of x times x, because we have only one variable here. If we had multiple variables, we'd have to do the matrix multiplication, so x prime x inverse 1 x prime y. And number 2 is the other one, the other estimator that we have. So I'll just quickly run it. So the 10,000 iterations are done. We can then move to the part D, where we basically plot these estimates and we see what they look like. Okay, so here is the distribution of the OLS estimator that we just generated based on our 10,000 repetitions, and we also have the mean plotted here in the red line, as you can see in my script. This is given by AB line, and then V equals to 1, and then column color is red. So you can see that the true value of beta was 1 that we set, and this distribution is pretty much centered around these, the true value. Now let's take a look at the distribution of the other estimator, beta tilde. Alright, this one is also pretty good. It is also, I'd say it's unbiased because it comes up with a pretty good estimate of the beta as well. So let's take a look at the average of the simulated estimates of beta, of the two different betas. And the average is indeed 1. So both of these estimators, the OLS estimator, which is the x prime x inverse 1 x prime y, and the alternative estimator that we're considering, which is using the x cube divided by x to the power 4 times y. Both of these estimators are unbiased estimators. But what we want to demonstrate here is that OLS is efficient. That means it's the best linear unbiased estimator, and that the best portion comes from being the one having the least variance. So what we're going to do is we're going to store the variances of the 10,000 estimates that we have for each estimator, and we'll take a look at the variances right now. And let's see, variance of the estimates of beta OLS is 0.04, variance of the simulated estimates of beta tilde is 0.05. So here we can see that the OLS has a smaller variance compared to the alternative estimator, and this is basically our representation of showing that the OLS estimator is more efficient than other linear unbiased estimators.
If you like my videos and find them helpful, then please support my work by subscribing to the channel.